All right, welcome to video two. Video two is going to walk us through a couple of these limit definitions in search for a pattern. I went ahead and did this function derivative or the derivative function already. I was given a function. This is the original function. I want to find the derivative. I set up the limit definition. Here's the difference quotient. I had to multiply this negative 1/2 to everybody. At one point, I noticed that just like before, this last term is going to cancel out. So we're left with this. I can factor out an h from the top, and those h's are going to reduce, and I get my final answer as negative x. So after you do a bunch of these, you notice, well, there's kind of like a similar pattern, right? Like I have to square this x plus h, and then if there's a number, a coefficient given to us here that we're multiplying, I got to distribute it, and then I know that the last term is going to cancel with something in the first part, and then I have to factor out an h, and then I can substitute the 0 in for h to do direct substitution to evaluate the limit. So we do it over and over again. We realize, well, we notice some patterns. The next example, though, that wrote out for you is not a square. It's actually a cubed. And the cube, I'm going to have to cube x plus h, which I did over here to kind of just remind you, when you're cubing x plus h, you're multiplying x plus h times x plus h times x plus h. So I multiplied these two, and I got this whole thing. And then I took each of these things, and I multiplied it times that, put it together, and we ended up with this. For those of you with a good memory, in pre-cal, we talked about the binomial theorem, how when you take a binomial, like an x plus h, to a power, there's a pattern, right? And so if you notice, x to the third, because the power was the third power, and then each term goes down 1 degree, x squared, x to the first, x to the 0, there's no x. And then the second term increases. We can talk about that later, but the idea here is we got x plus h cubed. So I came back and I quadrupled everything because it said 4 times x plus h cubed. So I multiplied everybody by 4. And once again, I noticed, oh, look, this last term is going to cancel with the first term. All of the leftovers have an h, at least an h in common. So I factor out an h. I'm left with this. These h's reduced. Now I can take the limit. I'm going to substitute 0 wherever I see an h, here and here. So those are going to go away. And I'm left with 12x squared. This is the derivative function for this cubic. And so we can continue doing a bunch of these. And we're going to find that those patterns are the same, right? Like I'm going to have to, if it's a cube, I'm going to have to cube x plus h. If it's a square, I'm going to have to square x plus h. And I'm going to go through the same process. So when I look at a table here that has the original, let me break it up this way. If I have the original function on the left side and the derivative function on the right side, do we notice any patterns? For example, where did this 10 come from? Where did this 12 come from? Can you look at the first column? Is there a way that I can get 10 by looking at the setup of the original equation? Well, what if I multiply this exponent times the coefficient there? What if I multiply the exponent times the coefficient there? Oh, then I get the coefficient of the derivative. And I even did that here because if you multiply 2 times negative 1/2, well, we get negative 1. But then if you notice the new exponent, what's the exponent here? This is x to the 1. It just dropped one level from the previous exponent. It went down 1 power. So this was second power, now it's first power. This was second power, now it's first power. This was third power, now it's second power. And this pattern that works with power functions are functions that are in the form of some number times x to a power. If I can set it up like this is a power function, and power functions always follow the same pattern, and we will be able to find the derivative function a lot faster. And that's what these notes are about. So if I go back to the original sheet that I gave you, the 2.5, 2.6 last week, we find that there is a power rule for power functions. And the power rule says, if I have a function that's x to a power, then the derivative is just n times x to the n minus 1. In other words, I'm multiplying n to the front as a coefficient to the x base, and then I'm subtracting 1 from the exponent because it's dropping down a power. So a couple of things. This only works for polynomials. This only works for powers of x. It doesn't work for e to the x. It doesn't work for 4 to the x. It only works when x is a base and my exponent is a number. Make sure that the x is in the numerator because the power rule does not work if my x is in the denominator. Now, how do I move something from the denominator to the numerator? Well, we introduce negative exponents, and that's what we're going to have to do here in a little bit. But just for fun, haha, and to finish this video, we're going to find the derivative of x to the third. Well, according to this rule, the derivative, I'm going to do it in blue, f prime of x, the derivative of f of x is, I'm supposed to take my exponent, multiply it times whatever's there. So that's going to be 3, because there's a 1 there, times x, and then I'm supposed to subtract 1 from the exponent, drop it down a power, and we get 3x squared. I guarantee you that this is the derivative. Not only that, if I want to find the derivative at a specific value, like they're asking me to, all I have to do is substitute that value in for x, and we're done. You just found the derivative value. You just found the instantaneous rate of change. You just found the slope of the tangent line in less than a minute. Does it work if I have a negative coefficient? Sure. Let's find the derivative. We're going to take the exponent. We're going to multiply it times the coefficient. Well, that's going to give me negative 6x. And then we're going to drop the exponent by 1. So if I drop it by 1, it's going to end up as negative 6x to the first, or just negative 6. That's it. If I want to find the derivative value at 3, well, then that would just be negative 6 times 3, and that would be negative 18. I just found my derivative value at that particular point. Be careful, though. Well, let's do f, and then we'll do, let's do g, and then we'll do h. So I'm going to zoom in. Is the power function, is the variable in the numerator? Because if it is, I can do this easy peasy. So the derivative is, I'm supposed to take my exponent and multiply it in front of as a coefficient of x. So that'll be 4x. I'm supposed to drop it down a power to the third, but there was a division by 6, so I'm going to create like a little fraction and say, if I'm going to put a 4 on top and I'm dividing by 6, and that's really 4/6, which is just 2/3 times x to the third. That is my derivative function, and I can now find a derivative value by substituting whatever x value you want. They keep wanting me to find the derivative at 3, so let's type in the derivative at 3 by substituting 3 into the input, and we're going to get our answer. Here I can say this is 27. 27 divided by 3 is 9, and 9 times 2 is 18. So I think this is the actual retail price. That's it. Not too bad. When I get to h, though, I got to be careful. I cannot do the power rule. Why? Because my x is in the denominator. So I need to move it to the numerator. So I need to be very careful because I'm only going to change the exponent from positive to negative when it moves. I also need to know, is this 4 exponent attached to the x, or is it attached to the 2, or is it attached to both? Because whatever the exponent is attached to, I need to take it for a ride, right? I need to flip it over and move it to the numerator. But it turns out that I'm multiplying 2 times x to the fourth power is only with the x. So before I start anything, before I take the derivative, notice I'm still writing in black ink because I'm not taking the derivative yet. I'm rewriting the way it looks in order for me to take the derivative. This would be x to the negative 4, and then on the bottom 2. So I can move a power of x from the numerator to the denominator or from the denominator to the numerator, as long as I change the sign of the exponent. Notice the 3 stayed where it was. It wasn't affected by this move. The 2 stays where it is in the denominator. But this power, if I'm going to use the power rule to find the derivative function, I need to have it in the numerator, and that's why I went up there. Great. Now I'm ready to take the derivative. What does the derivative power rule say? Take the exponent, multiply it times the coefficient in the front. That's going to leave me with negative 12x. And now I'm supposed to subtract 1. Be careful. Some students write negative 3, but that's not negative 4 minus 1. Negative 4 minus 1 is negative 5, all divided by 2. This is correct. This is the answer. It might not look the best, so what I'm going to do is I'm going to go ahead and divide this. Negative 12 divided by 2, that's negative 6. And then I'm going to go ahead and return this. Since it has a negative exponent, I'm going to go ahead and return it back to the bottom so that I can write a positive exponent. That is my answer. This is my derivative function. Can I evaluate it at a specific point? Yes, I'm going to evaluate it at 3. So that would be negative 6 divided by 3 to the power of 5. Ooh, 3 to the power of 5. I don't know what that is. Let's see. I guess I can cancel one of, there's 5 3's, right? 3 times 3 times 3 times 3 times 3. I can cancel one of them or reduce one of them with the 3 that is part of the 6, because 6 is 3 times 2. So I guess I can say this is really negative 2 over, I divide the top by 3, got negative 2. Divide the bottom by 3, I'm going to get 3 to the 4th. And 3 to the 4th is 3 times 3, 9. 3 times 3, 9. 9 times 9, 81. This is the slope of the tangent line at x equals 3 for this function that we were given. I'm going to pause the video here. I'm going to ask you to try some of these and bring them to class. Can you try number C, number F, E, D, I? Try L and try J for sure. And then in class, or I guess next week, we'll worry about the radicals and how to change radicals. But I think this is telling you how to do it, but we'll practice it next week.